Hi, good afternoon. I'm John Wilbanks with Columbia Southern University, and today we're going to talk about fire dynamics for a few minutes. We're going to list the 5 classes of fire and describe the fire growth process that it applies to the different types of fuel and classes of fires. We're going to talk about the similarities and differences between premixed and diffusion flames. We're going to explain heat of combustion and combustion efficiency. We're going to define the differences and similarities in the fire triangle and the tetrahedron, and we're going to define the dangers of smoke and how the different flames applies to smoke. So getting right into the classes of fires, there are 5 classes of fire. Class A is your ordinary combustible fires, such as ordinary materials like paper, wood, cloth, rubber, or household rubbish. Class B fires involve burning flammable liquids or gases. These liquids can be paint, gasoline, diesel fuel, oil, anything like that. Typically, Class B fires burn on the surface of the fuels, and sometimes if the mixture is right, the fire can burn within the area of the gaseous mixture itself. Class C fires involve energized electrical equipment. A C fire can also involve other materials burning, such as the electrical wiring or insulation that it's around it. Class D fires involve combustible materials such as magnesium, titanium, or lithium. And Class K fires involve cooking oils and some animal fats. Because of the use of newer, modern, higher efficiency cooking equipment and oils, the Class K was developed. We'll talk a little bit about the fire growth process as it applies to these types. Fire in itself is a rapid oxidization process, but we should always keep in mind that fire growth is not always an uncontrolled process. Fire is often used in many processes such as cooking or general industrial applications. There are 4 stages of fire growth: the incipient stage, the growth stage, the fully developed stage, the decay stage or period, and that's the end of the fire when the fire begins to go out. Fire growth is dependent upon materials that are available to burn always. Once ignition has occurred, the fire, if left unchecked, will transition into that second stage, the growth. Here, a Class A fire will begin to burn all the available materials, and it will consume those materials until the fire goes out. Certain fuels will burn more efficiently than others, however. A common Class A fire, for example, in the fire service is a furniture fire where we have polyurethane foam. Polyurethane foam burns very quickly and likely will lead to a very rapid fire growth. This pyrolysis of the solid fuel through the heating process rapidly breaks down the molecules into a gaseous form. Pyrolysis is known as the thermal decomposition of a substance into other molecules. Occasionally, some can melt or vaporize or transition from a solid into a gas in a process known as sublimation. Class B fires, they're typically seen horizontally over top of an ignitable liquid, such as when we see gasoline spilled. Typically, the heat of combustion or the amount of energy released is diminished when converting liquids during pyrolysis. As the flammable liquids begin to heat or vaporize, vapors are produced from the substance off the surface of the liquid. As the vapor reaches its flammable limits, the ignition of the vapors can occur. It is important to understand that vapors are a gaseous state of fuels. Gases such as propanes will fall into this Class B category. Gas is the physical state at a normal pressure and a normal temperature. Flammable gas will burn based on the flammability hazard of that gas. Once the gas has in effect burned off or the source is secured, such as when we close a valve, the threat of ignition has diminished. Class C fires, as mentioned before, they're energized electrical equipment. The materials that typically burn are the Class A materials that are there for the insulation or the associated electrical material. As the energized equipment is secured, the material will still burn. This material, such as the plastics or the rubber, will begin to decay and the fire will eventually be gone, or the fire will be extinguished. Class D fires involve combustible metals such as magnesium. These metals do not normally burn in a bulk mass. Solid metals tend to have their atoms very tightly bonded, and therefore oxygen cannot reach the atom. You couple this with the need for a higher ignition temperature, and this does not allow for complete combustion process to occur. They most often will burn in the form of dust or shavings. However, magnesium itself will ignite and burn in a solid form. Some metals, such as alkali, are reactive with water, and the higher on the periodic table, the more reactive these metals are. Magnesium is extremely volatile when water is applied. Combustible metals tend to burn hotter, faster, and more completely. Class K fires involve flammable liquids that are used in the kitchen application or the commercial kitchen application. These fires are similar to the B fires that burn the surface of the oil. Fires that are fueled by commercial cooking oils can only be extinguished typically by a Class A fire extinguisher. This process is known as saponification. Saponification takes place when the alkaline mixtures are applied to the burning cooking oil or fat, creating kind of a soapy foam on the surface that holds the vapor and the steam, and this is what will extinguish the fire. When we talk about premixed and diffusion flames, flames will fall into one of 16 different categories. Two flames that we'll discuss are the premixed and diffusion flames. Premixed flames are when the fuel and the air are uniformly mixed before the oxygen occurs. This mixture of air and fuel creates a highly combustible situation. An example of this is when the fire department is called to a residential structure for a gas leak explosion. Likely the air and the gas mixture had a flame introduced, possibly maybe by a heater coming on. When the premixed fuels then ignited, this caused the explosion. A premixed flame in a Bunsen burner would be blue when the flame and the air are mixed prior to the combustion reaction. In diffuse flames, there, as the name applies, the oxidizer and the fuel gases in a flame exist in two different arenas, and then they're introduced to each other in the combustion zone as the gases diffuse together. The premixed flames create little to no soot, whereas with the diffuse flame, this will create more soot. Both require an oxidizer and fuel mixture to burn properly, or to burn at all. Let's talk just a little bit about heat of combustion and combustion efficiency. Heat of combustion, as defined by Gorbit, Farr, and Rockwell, is how much energy a fuel can release when oxidized. Heat of combustion can vary with certain fuels, which means that specific amount of fuel brings a specific amount of heat. Combustion efficiency is defined as fuels that will not 100% burn due to the ambient environment. And the incomplete diffusion of oxygen, this is basically how well something burns. The similarities and differences between the fire triangle and the fire tetrahedron. The fire triangle has three sides: fuel, heat, and oxygen. This was a common way to describe the components required for a fire to burn. In this design, the theory is that you remove one side, you will put the fire out. The tetrahedron adds an important factor known as the sustained chemical reaction. The main difference is that you can still remove any portion of the tetrahedron and the fire will go out. However, this means that interrupting the chemical chain reaction is required in some manner in order for the fire to go out. When we talk about smoke, smoke is known as an irritating effect on the respiratory system. This can lead to hypoxia and death. There are many significant toxins such as hydrogen cyanide or sulfur dioxide that is present in smoke, and this can lead to long-term health conditions. Flame production can create smoke due to incomplete combustion. As fuels differ, the flame can burn cleaner or dirtier, if you will, such as when natural gas burns versus when diesel is used. The flame is present, but the hydrocarbons do not burn efficiently, and therefore more soot will appear. This completes our discussion this afternoon on fire dynamics. Thank you.